So, folks, what we've been building towards are these principles of superposition. And the first one that we want to talk about says, if we've got a linear differential transformation, what do I mean by that? I mean like this L that we described up above here, where this L sort of looks like the left-hand side of and this part's important, it's an nth order, it's a linear differential operator like we have here. Then suppose we have two different functions that when we do the linear differential operator to it, it outputs a 0. Notice this one did not output a 0 in this example up here. It outputted some function other than 0. But there are functions that I could input to have it output a 0. If I have two of those functions that when you plug them into the linear differential operator, that left-hand side of the differential equation, careful, not any differential equation, it needs to be a linear differential equation. And if we have two solutions so that it spits out a 0, then so will any linear combination of those two solutions. Now, proving that is actually a lot of work if all we're studying is differential equations. But because we're also studying vector spaces, we will eventually be able to show this in just one line. For the time being, I'd like you to go ahead and copy down the proof, even though we haven't discussed what a kernel is. But one of the reasons why we study vector spaces in this class is because using the language of vector spaces, some of the more difficult topics can be easily understood, whereas if we try to work with them just with our knowledge of differential equations, it would actually be a mess to try to prove these things generally. I'm going to let you guys copy down the proof, so pause the video, copy down the proof, and I'll meet you in just a moment. So the upshot of this proof that we've just looked at is it says that if y1 and y2 both solve the same nth order linear homogeneous equation, then so does any linear combination of those two functions. And now we're really getting the ball rolling here. So the first thing I'm going to do is just practice this. And I've done this a couple of times for you, so I'm not going to work through this again. But what I want you to point out, what I want to point out to you is we've already learned this idea of finding the characteristic equation. And the characteristic equation for this homogeneous differential equation is r squared minus r minus 6. And if we were to factor it, it factors as r minus 3 times r plus 2. So we get these two solutions. Y sub t is equal to e to the 3t, and y sub t is equal to e to the minus 2t. And I want you to verify that these both solve the linear differential operator that I've set here, set equal to 0. So go ahead and copy down the solution to that. It should feel a little familiar. We've done it a couple times, but thankfully this is our last time doing it, because up above here, we've proven that that will always be the case. But go ahead and work it out by hand one more time just to see how that works, because that proof is fairly abstract. And pause the video, work through that proof, and then I'll see you for the next principle. So now we move on to the second principle of superposition. And this tells us what to do when we have non-homogeneous equations. So we'll still take the left-hand side of this differential equation here. Oops, just the left-hand side. The left-hand side of it, and it is a linear differential equation. It's nth order. And we will call that left-hand side a linear transformation. Then, and this is where this gets more complicated, and we're continuing to build this idea, but we suppose we've got a basis for the homogeneous system. So that's what we're in the process of building right now, is this idea of a basis. What we mean by that is a collection. In this case, if this is an nth order ODE, we need a total of n vectors in our basis. So we need n solutions to the homogeneous differential equation. And they all, n of them, need to be linearly independent. If that's the case, and we've proven that the dimension of this vector space is n, if we have then n linearly independent vectors in that vector space, we have a basis for it. Okay. So that means then that we've got a general solution. And so if I lost you on that description about a basis, folks, hopefully we already have a little bit of a working understanding of what we mean by the general solution. And so if we have the general solution to that nth order homogeneous differential equation, and then suppose we've got one particular solution to the non-homogeneous problem, meaning notice here I've set the linear differential operator not equal to 0 like I have previously, but I've set it equal to the right-hand side of that differential equation, then we can say that this function right here, y equals y sub h plus y sub p, solves the differential operator set equal to our forcing function, and in fact it gives us every solution because every solution can be written in that form. And so for that reason we will call y equal to the family of solutions that solve the homogeneous equation plus one particular solution to the non-homogeneous equation. That combination is the general solution to that homogeneous ODE. So folks, that's a very complicated issue, but it really finishes up the work that we've been building for quite some time now. So please go ahead and copy down the proof of the second principle of superposition. It's not as lengthy as it might seem. Give it a shot, and then I will see you in the next video where we look at the consequences of that proof. So again, pause the video, copy down that proof, and I'll see you in a moment.